So welcome back to Question and Answers. So Giovanni is asking the following question. If I have a reactant or whatever, a configuration space and a region W, and I'm defining the propagator relative to the region W, as, for instance, the probability to start from xi, land into x without ever touching the region W. Well, this, we say, in the language of path integral was done by introducing into the path integral, along with the effective action or the Gonzaga-Markov fractional, depending on how we want to use the emission or non-emission form. Along with this, we introduce also a second functional, which we called omega, which was basically shooting to infinity if any point along the path this happened to be entering the region W. Now the question Giovanni raises is that, suppose I have a trajectory that spends only a limited time of its time extent inside W. Then I would expect that all that W does is to kill this part of the path and just leave outside this one untouched. So I'm just sort of reshuffling, giving weight to only a part of the trajectory and not to all. This is not correct. The reason even the slightest penetration into W kills an entire path comes from the fact that the path is actually a function in infinitely many variables, or in a very large number of variables if the system is discretized. So let's rewrite this expression in a form that is, remember, when in doubt, discretize. So the same propagator now is a collection, is an integral over a large number of intermediate time frame, y1, y2, dyn minus 1, or yn. Again, the boundary conditions don't matter. Then I have my Gonzaga-Markov functional, which is a function of yn, yn. Now, after discretization, the Gonzaga-Markov is simply a function of these variables. And then I have my additional boundary condition functional, which I can write the following way: sum over k delta t omega of y1 yn, right? Now, the omega y1 yn is a function that becomes infinite if in any frame this is entering omega. So after we discretize, we can think about this as, a very large number. Say, to make this explicit, I could give a more formal, abstract arguments, but I want the sentence that I'm making to make sense in a concrete example. So suppose, in order to implement this, let's take a large constant k, and let's take a product of characteristic functions of omega in each of the frame. So let's say, I'll say that this is my functional, right? So, in other words, what happens if my path is, so what is a path? A path is a specific choice of y1, yn. And let me bar it. That's my path. And what is the statistical weight of this path is the sum of these two functions, exp minus f of y bar 1, y bar n, and exp of this term here. Now, what happens if all of them are outside W? Well, this part here is what it is, and all of these parts in here, the exponent, the argument of the exponent is all 0, so this exponent is 0, 1. So if all of the y's, y1, y2, y3, 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 happens to be outside the region W, then the weight of this path is just a statistical weight of a standard Langevin trajectory. Now, let's now look at what happens if, say, only one frame is inside W. Then the weight of this path would be 0 in the exponent, 0, 0, 0, 0, 0, 0, k. Because here the characteristic function would be 1, 0. So this will be minus k delta t. Now, if k is infinite, if k delta t goes to infinity, this entire exponent, which is associated to the entire path, is exponentially suppressed. As a result of this, even if one slice is inside W, the entire path has a zero average, a zero measure, a zero probability density. I hope this answers the question, Rajan.